Okay, this is the third and final hour for Physics 1C for December 6th. And now what we're going to do is we're actually going to apply Maxwell's equations, Faraday's law, and Ampere's law to our plane waves and see what we get from that. So this is a picture over here on the left of how we're going to do this. I guess my question to you is this picture good enough? So shown in this picture are two different planes. One plane here, one plane here. These correspond to our plane wave that I was just describing here, where this is one plane and there's a parallel plane next to it. So this is looking at two parallel planes. The value of the electric fields that are shown here are supposed to be different, although it's hard to tell. Maybe that's why I ended up drawing my own picture. So like E is supposed to get bigger as we go from here to here. And B is supposed to get bigger as we go from here to here. Okay? Anyway, so that's our picture. Do you all want me to draw another picture? Or are we okay with that? That's the real question is, can you see how this picture follows from this picture here? That now, when we consider two plane fronts that are next to each other, they're going to look something like this. Or do you all want me to draw another picture and kind of explain it as I go? What do you want? I will do either. It does not matter to me. Draw it? Okay. So here's the idea. We've got these two different wavefronts, and to construct those, what we're going to do is we're just going to use just lines. So copy, paste, click, copy, paste, Control Z, copy, paste. There we go. All right, so here's going to be one of my wavefronts. And then we'll connect those lines up here and here, and then down here at the bottom as well. So there's my wavefront. Within my wavefront, I'm going to have electric and magnetic field vectors. So we really only need one of these. I don't need to draw two, but I'll draw two anyway. So we're going to have an electric field vector that looks like this. We're going to have a magnetic field vector that's perpendicular to that. We'll use blue for that one. We need to make it parallel to the plane. So there we go. So there's E and B, and then let's copy paste that down to indicate that all along the same plane, we're going to have the same values for these things. And then we need to take this whole thing, copy paste it, and then we need to put them parallel to each other. And now what I need to do is I need to make these smaller. Actually, in the picture, it's the other way around, so we'll make this one smaller. Go a little bit smaller there. Go a little smaller there. Same thing. That one stays the same. We just do the same thing with the magnetic fields, so a little bit smaller here. And all we're showing is the amplitude of a cross-section of the wave at a moment in time. That's what's being represented by these different plane waves here, right? At the end of the day, our wave, if I just look at it in two dimensions, okay, what are my dimensions here? This is y and this is x. In two dimensions, what I get is a wave that looks something like this, okay? Where at every point, the electric field vector is drawn like this. Right? So down here, this is my electric field vector, right? And what I'm showing here is a cross-section of a whole bunch of waves where we know the electric field at two different points, right? So again, you have to imagine that this thing, that you would have, electric field vectors over here, electric field vectors over here, and your own, you'd have a plane here, you'd have a plane here, et cetera, et cetera. That just kind of makes things confusing. Now, in particular, in the case of these waves, where we have, again, this is E, and this is B. This electric field that we're going to talk about is only going to oscillate up and down in the y direction. And the magnetic field is only going to oscillate in and out in the z direction. So really what we're looking at here is just the y component of the electric field, E sub y, and the z component of the magnetic field, bz. Okay? Same thing for both of these. And for this one here, I'm going to say, I don't know why your book doesn't do this, but I'm going to call this one EY prime, and I'm going to call this one down here BZ prime, to indicate that they have different, oh wait, what did it just do to that Z? Z prime. Okay. Now the next thing we want to do is we want to use Faraday's law. And Faraday's law tells us that if we take the integral of E dot dl around a closed path, that this should be equal to the negative of the change of the flux, right? Or if we want to write it out more completely, we could write the flux as being the surface integral of b dA, which is the way we're going to have to use it in this case. So how do we actually do that on our picture here? Well, the way that we're going to do it is that we are going to do a loop where we go basically like this. We're going to go this way, and then this way, and then this way, and then back again. That's our loop that we're going to use for this piece right here, okay? So let's do that. I lost one of my vector symbols here. So we're going to draw a box. And our box, let's use green for our path. Our box needs to be right here, and we're going to make it so that it lines up. I don't want to completely block everything out, but it's going to look something like that. Something like that there. This is going to be our path. And I think we're going to go around like this way. Let's see what B is coming out. Yeah, so okay, yeah. We want to go our path integral, we're going to go this way, and then this way, and then this way, and then this way. And we're going to say that the height is A, up and down. So this is A. This is just a choice. We're defining it to be A. And a width, delta x, because after all, the x direction is this way. So we can call this side over here to have a width, delta x. And really, that's kind of the distance between the planes, right? That's what delta x is. So we've got a path that has a length of A by delta x. It's rectangular. And we want to calculate E dot dl along that path, okay? Remembering that for the electric field for the wave that we're describing, it only has a y component, okay? So how do we do that? Well, the arrows that I've made on this path effectively represent our dl's, okay? So there's like a dl that goes that way, there's a dl that goes this way, so on and so forth. Also a dl on this side that goes up this way, and a dl on this side that goes down this way. So when I do E dot dl, what I'm going to be doing is, let's start here, okay? So starting from here, I'm going to write EY prime times dl. Because after all, on an individual wavefront, EY prime times this length, my bad. This length, which is A. We can do that because we know between 2 points on the same wavefront, going from here up to here, we know that the value of EY is the same all along there. We're calling it EY prime. That's just the value of the electric field here. So if it's constant, then we can pull it out of our integral here, right? Anytime if I'm doing E dot dl, and this is always going to be the case for everything we do for today's derivation, I can pull the E out, and we just end up doing integral dl, and the fact that it's a dot product here, and then this is how it just becomes E times A, basically, or something like that. That's what we're doing. So along this one, we have EY prime pointing the same direction as dl, so I get positive EY times A. Along the top path, the electric field would be pointing, I didn't draw it here, but along our top path, the electric field would be pointing like this, which means that it's perpendicular to dl, so that when we do E dot dl, which is E dl cosine of 90, we're going to get 0. So on the top path, E dot dl is 0. Continuing around our path, going down this way, now EY is up, but dl is down. You can kind of see that in this picture here, because in this picture here, it's kind of a side cutout of what we're doing, right? So along the left side here, dl is down, EY is up. So we're going to have minus EY times A. And that is the left-hand side of the equation. Everyone on board so far? The right-hand side of the equation, we need to find B dot dA. What we're going to do now is acknowledge the fact that the area of this entire thing is just A times delta x. we're going to say that even though the magnetic field changes as we go from this point to this point right here, we're going to assume that eventually we're going to make delta x really tiny, which is going to make it so that the average value of the magnetic field in this region, we're just going to call Bz, okay? And B dot dA is just going to become Bz multiplied by the area, which is A times delta x. So we're just saying in general that the magnetic field in this region, on average, is Bz. You could even think of this as being like an averaged value if you want to for Bz, but it's not really going to matter much. So Bz times A times delta x, right? So we get that equation, and now we're going to start manipulating things. We're done with the physics, if you can call it that. This is a very mathematical derivation. So before I move on, does anyone have any questions? Can you see how the left-hand side of the equation becomes EY prime A minus EYA? And can you see how the right-hand side of the equation just becomes B times area, right? Okay. All right. The next thing that we're going to do is we're going to say that EY prime we could define in a more general way, because the electric field in our case is going to be a function of x and t. Okay? The y component, this is kind of weird, the y component of our electric field is only going to vary in terms of x. It's not going to change as we move up and down. It's not going to change as we move left and right. It's only going to change as we move in the x direction. So our goal really is to figure out what this is. So EY prime, we're going to write as EY, the value of EY evaluated at x plus delta x comma t. And then just what we had as EY before is going to be the value of EY at x comma t. Okay? So that the left-hand side of my equation now, acknowledging that these a's all cancel, the left-hand side of my equation now is going to become, instead of EY prime, that's the value of EY at the location of x plus delta x. X is the left-hand side, x plus delta x is the right-hand side. So the coordinate of this side right here is x plus delta x. So EY prime becomes EY of x plus delta x, comma t, minus EY, which is just going to be EY of x, comma t. We're then going to divide the entire thing here by delta x. Why can't I just write straight? There we go. Divide by delta x. Right? Do I care about where the minus sign is? I don't think I really do. And then the left-hand side is now going to be ddt of Bz. Although, at some point, this is going to have to become a partial derivative. You might as well go ahead and do it now, so you're all not wondering why I waited so long. Why is it a partial derivative? It's a partial derivative because Bz is a function of x and t as well. So if I want to take the derivative with respect to time, I'm going to have to take a partial derivative, right? Okay. The left-hand side. Now what do we do? Well, the next thing we're going to do is we're going to take a limit as delta x goes to 0. And the effect of that is going to be that this entire left-hand side is going to reduce down to a much more simple expression. What does this thing on the left-hand side become as we take the limit as delta x approaches 0? We have 30 minutes left. I think we can finish this in 30 minutes. It's the derivative of e, not with respect to time, but with respect to x. If you go back and look at the definition of the derivative from really early on in your calculus textbook, this is the definition of what a derivative is, except that early on in your math textbook, they wouldn't have two variables for your function. It would just be one. The fact that there's two variables here means that this is technically the definition of the partial derivative. Del ey del x is equal to negative del bz del t. That is that. There's no constants, nothing else, just the time rate of change of the magnetic field related to the time rate of change, the space rate of change of the electric field here. Okay? Okay. Next, we need to do the same thing in the xz plane for Ampere's law. So we used Faraday's law already. We're done with that. Faraday's law basically turned into this, right? For our plane traveling electromagnetic wave, our Faraday's law has now become this. So this is our new Faraday's law. Very specific to our very unique setup that we have here. Okay. The next thing that we want to do is we want to do the same thing for Ampere's law. Okay. And that's represented here. So for Ampere's law, what we're going to need to do is we're going to need to flip it. Do we need to flip it? I could almost use the same picture. Not really. We'll draw it again. Okay, so for this one, again, we're going to need two planes. So here's our first plane. And then connect it up. And now we've got our magnetic fields, so we'll copy paste, separate these by a little bit. Okay, and now we've got our fields. Maybe I can just copy paste these pieces at least. Okay, let's just copy that thing. Copy paste, drag. Okay, got a little extra. Okay, so we've got this one, copy paste. That one, and grab both of them. Ooh, what did I do? And then we'll just make them both bigger. Maybe move this one down a little bit. Kind of try to line them up eyeball-wise there. Okay, so same setup. Two wavefronts that are next to each other that have electric and magnetic fields that are oscillating in them. For our electric field, that's this one. Again, it's just the y component of the electric field. This is the y component of the electric field at a different point in time. On the other point, we have BZ. And I think based on what we're going to draw next, let's put this like this. Z. There we go. And this will be BZ prime. BZ prime. Okay, and now what we want to do is we want to use Ampere's law. And Ampere's law states that if we do the integral of b dot dl, that this should be equal to mu naught epsilon naught times the time rate of change of the electric flux There we go. In free space means that the other term, which would normally be here, which is mu naught times I enclosed, the one that we originally learned. Free space means no currents. So no currents are producing magnetic fields. All right, so now what we do is we do b dot dl here. That means we need to construct a path. So let's do that. So our path in this case is going to be coming out of the screen. Let's see if I can do this. We'll connect this and this. We'll make this green. I said make it green. There it goes. It did it. Okay. And now what we'll do actually is we're going to move these around a little bit. So this needs to be kind of like here, right? So we'll do that, and then what I'll do is I'll just go grab all this stuff. Not this though. Dang it. I just want to grab this stuff. Well, let me if I no. It really wants to grab that. There we go. I think I got it. Copy. No, cut. Paste. Let's line it up right there. There we go. That looks good. And then take this one, copy paste, move it kind of out this way, and then link everything up. So now we need a line for our path that's parallel to this one. And a line for our path that's parallel to this one. And we put them together, and it should line up, and it kind of does. Cool. So there's my path. And let's see, electric field's going this way, so I'm going to go around my path this way. So this is going to be my DL here. On this side, it's going to be here. On this side, it's going to be against the grain. DL will be this way, whereas BZ's coming out. And then over here, DL like this. We'll use the same type of things we used before. So we said delta x was the distance between the wavefronts. So that's going to be the length of this side right here. And then we say the other side is A. So A will basically be this length right here. Now we do integral B dot DL. We can start wherever we want. I guess we'll just start at this point right here. So along this side, we're going to get, you all tell me, now that we did this already, what am I going to get? As I move along this side here, what do I get for B dot DL? What should I write down? We're coming along our path. We're going this way. Then we're going to go this way. Then we're going to go this way. What do I write down along this edge? Is it going to be negative BZ times A, positive BZ times A, BZ times DL? Is it going to be B squared over 2? What are we going to get for B dot DL? BZ times A, that's correct. So we get BZ times A, because BZ is going this way, A is going this way. We assume that our magnetic field only changes in the x direction, which means that the value of the magnetic field here and here and here is all the same, because that is the z direction going this way. Okay, so then we come to this piece over here. As we move in this direction here, we realize that the magnetic field in this region should be pointing kind of like this, which is going to be perpendicular to DL. So we'll get 0 contribution on this side, 0 contribution when we get to that side. It's only this side here where DL is going this way, but BZ prime is coming out of the page. So again, we're going to get a minus BZ prime multiplied by A. And that's the left-hand side. For the right-hand side, we're going to get mu naught, epsilon naught, EDA. Again, we're going to simplify this by saying we're just going to take kind of the average value of the electric field in this region, which is called EY, and multiply by the area, which is again A times delta X. Okay, that's kind of shown in this picture here, where the electric field is going this way. Our loop is going in this direction here. So this is our, this is our dA, is this whole area right here. And the electric field value there is just EY. And so there we go. Once again, we'll make a similar thing that we did last time. Instead of just writing this as BZ, we'll acknowledge that BZ is actually a function that varies in space and it varies in time in the x direction times A. Of course, there's an A on both sides of the equation, which we can cancel out. Minus BZ prime is going to be the value of, this position here is like X. The idea is that you've got a coordinate system where this is the Y direction and this is the X direction. I probably should have drawn this to begin with. This is the Z direction. So the position of the left wavefront is X. The position of the right wavefront is X plus delta X. So BZ prime, which is the value of BZ at this wavefront here, which is at X equal to X plus delta X, is going to be BZ of X plus delta X, comma T, equal to mu naught epsilon naught times EY. And then we just divide both sides by delta X again, and use the same technology from before to say that the limit as delta X approaches 0 of the left-hand side of this. Well, we're varying X, and the difference here is that the X plus delta X should be the negative in front. So what we're going to get out of this one is going to be negative del BZ del X. Oh, and I left something else off here. Whoops. Going from here to here, I left off the ddt. So there was a ddt of here, of this. And then when we come to this line, we'll change it to del EY del T. So del EY del T. And so our final result is negative del BZ del X is equal to mu naught epsilon naught del Ey del T. And what this has done is it's given us a simpler version of the Ampere-Maxwell law to use, or we'll just call it Ampere's law. So there we go. Anyone have any questions? Notice that this equation doesn't have a negative sign in it, but you get a negative sign, whereas Faraday's law has a negative sign in it, and you ended up with a negative sign. Those negative signs are now going to go away, but it's just interesting. All right, so now let's take these two equations. This one and this one. Why on earth would I do that? All right, so we've got our two equations, right? Let's get rid of these lines. Now what we want to do is we want to see how they fit together. You can see that there are similarities and differences between these equations. Both of them on the left side, you've got a del x, and both of them on the right side, you have del t. But they apply to different things, so we can't just plug one into the other one, right? Like del Ey del T doesn't show up in this equation. So we need to do something else here to make these equations able to merge into each other. And then the way that we're going to do that, I don't think it matters what order we do this in. I think it always works out no matter what you do. So what we're going to do is, which is the one that doesn't have this term on it? It's the b's, right? These ones. Okay. So we're going to make those equivalent to each other. What we're going to do is we're going to take this entire expression right here, and we're going to take del t of the whole thing. We're going to take the partial with respect to time of this one, and we're going to take this equation over here, and we're going to take the partial derivative with respect to x. The left-hand side of our equation over here will then become the second derivative of Ey with respect to x. This will now become a mixed partial derivative, negative del bz. The way we write these is you put a 2 right here, and then it's a mixed partial, so you take, what is it? You put del x and then del t down here. For this one, left-hand side, we're going to get negative del 2 bz del t del x. And on the right-hand side, we'll get mu naught epsilon naught, second time derivative now of this. So del 2 Ey del t2. And now you can see that if you know something from your mathematics classes, you know that it doesn't matter what order you take the derivative in. Does that sound familiar to you all from your Calculus 3 class? These two are equivalent to each other. It doesn't, if I have a function, right, of x and y and t, and the variables themselves are independent from one another, which means that the x is not a function of time and the time is not a function of x. I think I'm getting these details right, although I might not be. Then, it does not matter what order you take the derivatives in, you will get the same answer. I can give you a really simple example of this, just to make it clear what I'm saying here. Suppose that I tell you I have an equation bz of x and t, and I say that it doesn't matter what I pick, I guess. So let's say that it's like x squared t cubed plus the sine of kx plus omega t or something like that. K and omega are just going to be constants, okay? So if I take del b z del, let's do this one first. This would say take del x first. What do I get? The derivative of this with respect to x is going to be 2x t cubed plus the derivative of this with respect to x is going to be k times the cosine of kx plus omega t, right? And then if I take the derivative of that with respect to time, so if I do del 2 bz, then we do del x, I don't even know what the right way to write it is, honestly. Something like this. I guess you just pick one. If I now take the time derivative of this whole thing, I know the best way to write this. The best way to write it would be to use parentheses. So write it like del t of del bz del x. There we go. This is the same thing as del 2 bz del t del x, something like that. Okay? Take the time derivative of this, we're going to get 3 times 2 is 6xt squared, plus the time derivative of this thing is going to be k omega negative sine of kx plus omega t, I think. Does that seem right? Does everyone agree? Take a look at this. Does that feel right to everybody? Did I go through that too fast? It makes sense? Okay. So now let's say that we do the same thing, but we do it in a different order. The claim is that you're going to get the same answer. So we go over here, and we do it in a different order. So we start off with the same function, right? But now what we do is we're going to do del bz del t first, okay? And this is going to be, it looks like 3x squared t plus omega times the cosine of kx plus omega t. And then we now take the x derivative, which is equivalent to saying del 2 bz over del x del t. Then this is, the x derivative of this is going to be 6, oh, I made a mistake, sorry, this was squared still, because we're taking 3t and it's t squared. Sorry about that. So bring this down in front, you get 6xt, and now pull the k out, plus k times omega, but when you take the derivative of cosine, you get negative sine. And those should be exactly the same, right? Yeah. These two are the same, right? So that is to say that these two, this one and this one, are the same. That's my, it's not a proof, it's just an example to show you that it does work. But you probably learned that in your math class anyway, right? That these two are equivalent to each other? Is that something you learned in math class? Probably, right? Maybe you don't remember. Maybe you haven't learned it yet. I know some of you are in Calc 3, though. Okay. So, we know that they're equal to each other, which means that the other things are equal to each other too, which means that this is true. If we take the second partial of EY with respect to x, that is equal to mu naught multiplied by epsilon naught multiplied by del 2 EY del T2. Now, this is a differential equation, right? It's an equation that involves the derivatives of a function. In fact, it's a multivariable differential equation because this is a function of x and t, and this is a function of x and t. It's the same function, right? So the goal here would be to say, what is EY equal to? And this equation allows us to solve for that because it has a general form that we recognize as what's known as a wave equation. If you've taken Physics 1b, you've definitely discussed this. If you haven't, what the wave equation tells us is that if I want to describe a wave on a string, for example, okay, and I'll just give you a setup for this. Suppose that I have a coordinate system, and along that coordinate system, I have a rope that's attached between these 2 points right here. But this point is free and this point is fixed, so I attach a rope right here, right? And I tell you that this direction is the y direction, I tell you that this direction is the x direction, and then I take my rope and I lie it between these 2 points here. Like I say, I fix it on this end here, and now what I do is I oscillate this up and down in this direction, up and down and up and down and up and down. What will happen is that a wave will form on the string, and it will basically start to kind of vibrate up and down, right? With the speed moving in this direction here. And what we learned in Physics 1b is that there's a connection between the motion in this direction, where we can say that if we take del 2y del x2, that this is equal to del 2y over del t2, but this whole thing has to be multiplied by 1 over v squared. Okay? And we call this also a wave equation. You can see that it has exactly the same form as our equation here, right? Partial with respect to x, second partial with respect to t, equating them to each other, right? So what Maxwell realized when he looked at this is that, oh, this piece right here has to be the velocity. So he said, well, that must mean that the velocity of my wave should be equal to 1 over mu naught times epsilon naught square root. And as I showed you, I think 2 classes ago, this happens to be exactly equal to 3 times 10 to the 8 meters per second, which is the speed of light, c. So we've effectively proved that Ey is a function that fits into something that's called the wave equation, and as a result, we know what the solutions look like. The solutions to my equation are any function Ey of x comma t that's equal to something where Ey is a function of x minus vt. Any function you choose, it could be, for example, just as an example, Ey could be equal to 1 over x minus vt whole squared. You can check for yourself. Do we want to check? Maybe we want to check that this equation will satisfy this differential equation because it has the general form that it's a function of something x minus vt, and it guarantees that it will solve this equation as long as it's a function of x minus vt. Do you want to see how? Do we want to do it real quick? Maybe we do. I don't know how much time we have. We don't have much time, so let's do it anyway. So I'm going to prove to you that this, and any function in general that has this form, it could be 1 over x minus vt cubed, it could be 1 over x minus vt to the I times pi, it just doesn't matter. Anything that has this form, right? It could be the one that you're going to see most frequently is going to be looking like this. We're going to talk about sinusoidal waves, and the equation we're going to get is going to look something like this, where omega is the angular speed and k is this. This will also satisfy the wave equation. We can test it. But let's prove that this one satisfies the wave equation first, okay? Oh, and I don't know if it goes without saying, probably doesn't. We found this equation by taking the derivative of both of the sides to make it so that we eliminated bz. It turns out that you can get the exact same equation for bz. So the magnetic fields and the electric fields both satisfy this wave equation. You can find this wave equation in a lot of things in nature. That sounds correct to me. Yeah. All right, so let's see if it satisfies it. All right, so we're going to check. Check. But we've basically proved it, right? We've pretty much proved that when you take Faraday's law and Ampere's law and apply them to this kind of plane wave, you get a wave equation, which means that this was an accurate way to think about it. These waves are, in fact, oscillations of electric and magnetic fields, and it shows up right there in that equation. Okay. All right, so let's check to see if this satisfies the wave equation. Okay. So what is del Ey del x going to be? Well, our equation, let's write it in a simpler way, is basically x minus vt to the negative 2 power, right? So let's use that. Then del Ey del x will be negative 2 times x minus vt to the, add 1 to the power? Negative 1. And then if we, wait, you subtract 1 from the power, right? It's been a while. You subtract 1 from the power. There we go. If I then take del 2 Ey del x2, we're going to get negative 3 times negative 2 is positive 6 times x minus vt, and then we have to reduce the power again, so we get negative 4. Okay, so that's del 2 Ey del x. Let's do the time derivatives now. So for the time derivatives, we will have del Ey del x oops, del t. So the time derivative of this one will be negative 2 x minus vt to the negative 3, but then we have to multiply by negative v, so times negative v. When we then take the next derivative, del 2 ey del t2, then now we're going to have, so this would have been negative negative, so negative 3 times negative 2 times negative v, and we're going to get another v out of there, so I think what we're going to get is 6v squared x minus vt to the negative 4. And now let's see if I got the symbols right. So this was positive, and then we brought down a negative exponent, but we also multiplied by another negative. Yeah, it looks right to me. So it does satisfy it, right? Because if we look at our answers, and we look at our wave equation, right? Easier to look at this one over here. If we take del 2 ey del t2, and we divide by velocity squared, then these are equal to each other, right? So the way that we should have written this then is basically if we write 1 over v squared here, and we put 1 over v squared here, boy, that was weird the way that happened. It's probably because I have my thumb on the thing. Anyway, the point is, now, I wish all that stuff hadn't become, man, this thing's getting really unresponsive. Definitely time to end class when these things just stop working like this. Okay, so we put a 2 right here, and then we'll just make all this stuff green again so it doesn't look so weird. All right, there we go. Okay, so can you see then that these are equal? Which verifies that it satisfies the wave equation, and that any function of this form will automatically satisfy the wave equation. They can also have this kind of form as well. It'll also work. So that's it. Light is an electromagnetic wave, and we've basically proved that that's the case by showing that the electric field satisfies the wave equation, which was well known by that point. I mean, by the time Maxwell had done this, to him, seeing this solution here, for him, when he looks at that, he sees a wave, you know? That's what he sees. He just sees a wave. Because that's what we know in physics, is that when you have this equation, it embodies a traveling wave, a wave that travels through space. So we'll talk more about this stuff next time. We're specifically going to talk about sinusoidal electromagnetic waves. We'll talk about radiation pressure, the way in which light itself can exert pressure and momentum, and finally talk about the pointing vector. Then we'll watch that video from Veritasium about the pointing vector and the way that energy is transported around in circuits, and what we'll decide at that point whether we believe it or not. Okay, so there we go. Anyone have any questions or comments? If not, we are done for today. Yep, you're welcome. I'll see you all next time. You have lab this week. Be sure to come. If you don't, I'll see you next Monday.